In this work, we pursue a research that started a few years ago, where we tried to create a more suitable mathematical model for the photometric stereo approach, which is a basic approach for the 3D shape reconstruction. In this case, in this work, our contribution is basically divided in three main points. So the first one is to unify the specular and diffuse reflection given by an heterogeneous scene. So you can imagine our images acquired for the 3D shape reconstruction using biphotometric stereo, where you have a static scene with a static camera, and a set of light sources is changing, so you have a different shading information coming from different images. And if we have also an heterogeneous set of objects, you can have a specular object and a Lambertian object. We want to unify this kind of reflectance equation into a unique framework. The second contribution is the unification of the information, again using the image ratio. And then finally we want to solve this new approach using a minimization method based on L1 norm. So how we formulate the unified irradiance equation? We extend in some sense the well-known Blimfong model. If you want to know more about this kind of models, physical model, please come to the poster. I will be happy to give you more details about that. So where you have the albedo, the attenuation, and you have basically the inner product between the normal of the object n and the vector h, which is basically the combination between the light source and a sort of another term that depends on the viewer direction. And everything has to the power of c, where c is the Saninist parameter. Basically, when c is equal to 1, we are dealing with diffuse reflection, and when c is less than 1 but greater than 0, then we are observing a specular object. So starting with this kind of equation, of this irradiance equation, we derived a new model by merging a couple of equations. So in particular, if you consider equation given by the light source I and the equation and the image given by the light source J, then we divided both, and what we get is the quasi-linear equation, which is given by the scalar product between the vector field Bij, which depends on xy but also on the depth z, times the gradient of z, and this is equal to s. So these mathematical parts, I won't go into detail now, of course, but still, if you want to know more details about this mathematical part, just come to the poster. So why this operation of ratio? Just because it gets rid of nonlinear part like the normalization of the normal vector and also the albedo. So this is an approach which is albedo independent. How we solve this kind of problem? We just consider all the pairs of images, we consider the ratio, and we stack everything inside a very big linear system now, or quasi-linear system. So at the end, we are able to compute the depth using the minimization method. So where our functional to minimize is this big system, which is basically a set of quasi-linear equations, and we can also compute the Saninist parameter that tells us how much a surface is specular or Lambertian. So we perform a set of tests on the BRD on the Merle dataset, where now you can see on the x-axis almost all the materials. Basically, they are mostly specular, and you can see that if you do not perform an automatic search of C, then the approximation of the surface will be surely bad, and you can see in the channel colors. So as long as you increase the number of images and you leave an automatic computation of C, then the reconstruction will be much better. As last, I'll show you a reconstruction on real data, where on the Egyptian sculpture you can get a reconstruction because it is actually a Lambertian case, but on the upper case we can get a very good reconstruction using on specular, related to specular surfaces with respect to the existing to the existing approaches. So thank you.